Alright, cool. So, a bit of odd timing for this one, but we're going to be looking at flexural behavior of reinforced concrete, the three stages of, I guess, reinforced concrete, and then at the very end, I'm gonna go through design steps as well. So, pretty much similar to what you did in steel, is like pretty much, like if you have a custom section, like you're pretty much making your own section in this case. Like you're gonna have like a rectangular section. You're gonna figure out what the base has to be, what the depth has to be, and the amount of rear that you need as well. He's just joined. Oh, Liam. Hello.
Hi.
Cool.
Liam doing concrete.
I'm studying surveying, but I'm just gonna hang out.
Oh, okay. This is being recorded, by the way, Liam.
Oh, cool.
Yeah.
That's good.
Okay.
I'll refer to it next year.
Okay. Perfect. Okay. Cool. So I'll quickly run through the summary that I made at the very start. So the three stages are uncracked elastic stage. So when it's still elastic, it hasn't cracked yet. And like there's something I'll explain later on. When you know when it will crack or like at what point it cracks. That's what we call the cracking moment. Um, the second stage is when it does get cracked. We call it cracked, and the third stage is ultimate. So whenever we do a design for a concrete section or a concrete beam, we use the ultimate stage to do our designs because it's like with the worst case scenario, um, that's like at its weakest point. And yeah, all the calculations is something that I'll go through later on. And what I've done for for your guys' sake, is to pretty much just, what I've done is like made like a list of steps of how to kind of do a question and like do all the calculations and then eventually get to the final answer. That's something that you can expect in the final exam. Cool. So I've kind of illustrated what it looks like. There's a few key features that I'm going to go through really quick. You've got your neutral axis, which stands, the NA stands for neutral axis. That is pretty much where your centroid is. And this DN is what we call the distance to the neutral axis. Obviously we've got our top and bottom reinforcement. Depending on like how it's bending, it can either be compressive or tensile steel. Let's say for a beam that's bending like this, right? Our top steel is going to be in compression. Our bottom steel is going to be in tension. Cool. Let's get rid of this really quick. And then as you notice that, something you will notice is as you move along the stages of reinforced concrete, what will happen is that your neutral axis will slightly shift higher and higher, right? The explanations for that I'll kind of give as I go through each step. Now over here I've got like a strain diagram. For your elastic stage is pretty normal. For this one, oh yeah, by the way, for your strain at the neutral axis, your strain is always 0. Right? There's no strain, and the only key difference is in the ultimate stage, your concrete ultimate strain is 0.003. This is a very important number that we're going to need later on, so I'm going to highlight it. Something we're going to need later on. Now, strain, not too big of a deal. The only important thing is this. Stress is a bit important as well. It's actually really important. So I'll kind of explain what goes on. But this is what our stress distributions kind of look like. So for your elastic stage, you've got both compression and tension. For your concrete, when your concrete actually cracks, what actually happens is that the tension part of concrete, it has 0 strength. So it provides 0 strength to the overall, section. So we just ignore the tension in that case, and we just consider the compression. When it gets to the ultimate stage, you actually get a nonlinear distribution, right? So at one point, what you're gonna have to do is you're gonna have to calculate the force of this, stress distribution, which obviously for a nonlinear distribution is really, really hard. So what the AS3600 has, they've got two factors called gamma and alpha 2, which kind of simplify this kind of simplify the way we're gonna find our forces in the ultimate stage. Okay. Okay, so this is what I wanted to talk about really quick. So, let's say at uncracked elastic, you've got like 0 moment, and then as the moment that's being acted on, let's say your concrete beam increases, once it reaches a value called cracking moment, that's when your concrete actually cracks, okay? And then you keep increasing the amount of load being that's acting on the beam. The moment increases, and so you end up reaching something called an ultimate capacity. In terms of design, we kind of, there's one rule. It's similar to what you've done in geotech or like steels, where you've got a reduction factor, then mu has to be greater than or equal to m star. So m star is like what's acting on that actual beam, and phi mu is your design capacity, right? I've kind of gone through this in my crash course, so I'm not going to go through it again. But pretty much before this, your beam actually doesn't fail. Let's say I've got a reduction factor here. Before this, it's not considered to fail. After this is like when it fails, right? It gets fully cooked and then just gets destroyed. For the purpose of designing for strength, we only care about mu for now. So that's week 5 content. Yeah, so flexure. MCR, IEF, IG. So IEF is your effective second moment of area. I'm going to touch on that in week 8 because it's used for serviceability. So when we're thinking about the deflections of a curve, that's when it actually really matters. Okay, for now, it's not too important to us at all. Same thing with cracking moment. Like, the only important thing is if they ask us, oh, does this section crack, right? Depending on how much load is acting on it and the actual like value of MCR, that's probably the maximum they can ask you. Later on, we actually use this value to figure out some other things, right? And it kind of directly affects our IEF as well. IG, yeah, it's not really used that much, but there are some questions on this, so I'm going to go through like an example anyways. Okay, cool. That's like a brief overview of it. I'm going to kind of go through each stage now. Stage 1, the uncracked elastic stage. So this is what my cross section looks like. This is my strain distribution and this is my stress distribution. So actually normally, so what I've done actually is I've considered that the steel areas are the same, right? That's why my neutral axis is like right in the middle. However, the neutral axis will shift towards the heavier side. So what I mean by that is, let's say I've got my concrete section like this. I've got only tensile reinforcement. And let's say this is the middle of the concrete block. My neutral axis will lie somewhere below it. So this will be my neutral axis here. So like, because it's a, I'll actually show you guys how to figure it out. So this is a bit of a revisit to Eng 2400, but it's something called the modular ratio method. So depending on like which side has like more area or more mass, your neutral axis will shift towards that way. You kind of see it in the formula as well. So, but before that, I want to go through a few key values that you guys have to know. So, so this is my concrete section. This is my tensile steel, and it has an area of AST. Similarly, the compressive steel has an area of ASC. So first, so the AS stands for steel, and the C stands for compression. ASC, you'll kind of see this quite a lot. So you would be like epsilon CU. The C will stand for concrete, U will stand for ultimate. Alright, like this kind of convention is something that we see quite a lot. Another couple of things, DSC, DST. So DSC stands for the distance to the steel in compression. So this is comp steel. Is it still recording? Yeah, okay, good. And DST, we're taking a look at the tensile steel. Now, a key note, by the way, is we're not taking it to the top of the steel or the bottom of the steel. We're taking it directly in the middle, right? So I've got like a dotted line there to kind of show you that it's kind of, we're taking the distance to the center of the bar, right? Same thing with this as well. We're taking to the center of the bar. Now, the question that does arise sometimes is, what if we have more than one layer of steel, right? If we have more than one layer, so for example, we've got something like this. That looks hella weird. Let me fix it up. Something like this. So we've got 2 layers of tensile steel. Where do we take DSC? Do we take it to this upper one, this lower one? What do we do? The answer is you actually take the average. So you take it right directly in the middle, just like this. This would be DST, right? In between both of the centroids of the bar, right? Now later on, we're going to get introduced to another, what's it called? Value called D0 or DO. So some people kind of get these two mixed up because when we're working with singly reinforced concrete, so just one layer like this. Actually no, D0 I'm gonna touch on later. Actually, yeah, I don't even know why I'm touching on it now. Okay, don't worry about it. I'll come back to it. Alrighty. Anything? Oh, okay. Obviously, B is going to be our width, D is our depth, and DN I covered already is the distance to the neutral axis. Okay, now a quick touch up on some modular ratio method. So I think some people who did Eng 2400 during mech school doesn't know what this is, but if you did it with the civil school, surely you know what this is. It was covered in week 5, elastic and inelastic beams. And it kind of, the first thing that's kind of introduced to you is, let's say, okay, I'll kind of go through what modular ratio method is, like, really quickly. So, because it's really, really relevant to what we're doing in this course. So, we've got 2 different materials. We've got concrete and we've got steel bars. When we try find the moment of inertia, for something like this, what we're going to have to do is we're going to have to convert this, steel into concrete, right? So we multiply by a factor, which is determined by the stiffness. So a bit of an example that I remember back from 2nd year, does that even make sense? Wait, let me think. Like, it kind of doesn't make sense, like, if we don't convert this in, like, if we do the moment of inertia thing with 2 different, like, materials. Like, imagine you have, like, jelly attached to, like a brick. If like that's good enough, right? Like, because of the difference in stiffness, like one's like not stiff at all, like it just falls right off, and the other one's like really, really stiff. Like it kind of doesn't really make sense. But what I'm trying to get to is you're gonna have to transform your section. So you're gonna have to find an equivalent amount of steel, equivalent amount of concrete to this amount of steel. So, okay, I'm going into too much theory. I don't want to go into it anymore. But N is like your factor, and you take your ES of EC So ES is our elastic modulus. Elastic modulus of steel, and this is the elastic modulus of concrete, which means I'm converting the steel into concrete. And usually this number is like approximately like zero. No, what the hell? Not zero. It's usually like somewhere between. Like unironically, it's somewhere between 6 to 7. Unironically, like it's not even a joke. But anyways, pretty much what I'm doing now is I find this value of n, and then to transform my steel into concrete, I multiply it by this factor n minus 1. So I find n, let's say n I get to be 6.5, and then therefore, like I just need 5.5 here, and then that pretty much converts our area of steel into like some concrete, an equivalent amount of concrete, sorry. Okay, now from there we're going to calculate dn using this formula, and then calculate ig. So this is just deadass just 2400 recap. So I'm going to go through an example for that. But before that, I'm going to talk about cracking moment really quickly. So cracking moment, as I said earlier, cracking moment is the point at which your concrete cracks. So let's say I've got MCR is equal to, let's say 60 kilonewton meters. Let's say on a certain beam, after you figure out like the moment acting on it, you say that M star, the moment acting on it is 59 kilonewton meters. Because MCR, the capacity of my beam before it cracks, is greater than what's actually acting, I'm going to consider my section to be not cracked, my beam to be not cracked. However, if this changes to like 100, because M star is greater than MCR, my beam is now cracked. Does that make sense? Whoever's listening? I don't think anyone is. Okay, that's cool. But
Wait, no, can you just say that again?
oh yeah, of course. Okay, someone is listening. So MCR, let's say I've got the value for it is like 60 kilonewton meters. So you do all this calculation and you get 60 kilonewton meters. Cool.
Yeah.
Let's say on a certain beam, what's acting is 58 kilonewton meters. Okay.
Okay. Yeah.
So MCR is the capacity before it cracks. So as soon as it hits 60, it's got the beam's gonna crack. The section's gonna crack. Okay. So now in this case, because it's less than 60, it's not gonna crack. Yeah. But however, if this became 100 kilonewton meters, it's exceeded MCR, therefore it's gonna crack.
Yep.
Yeah. Beautiful. So that's what we call a crack section, or the cracking moment. A couple things in this, like it's looked into more in serviceability. Like, it's not too important right now. Just take this as 0. It gets a bit more techie later on. This, they usually give it to you, or you can calculate it using 0.6 square root of f dash c. You're gonna have to find dn and ig. So I think the best way to explain how to do these two is with an example. So let me pull up an example. This is from your workshop. So okay, I'm gonna try to explain just part A. Okay. So they're saying find the centroids. So this is dn. Second moment of area, that's ig. The cracking moment, MCR. Now, luckily for us, they've already given us ES. Oh no, ES is always 200 times 10 to the power of 3. They've given us N, and they've given us FCTF. So this, we're going to need for MCR. This, we're going to need for DN and IG. Okay. Okay, cool. First things first, they've already taught us that step 1 is to calculate n. So n ES over EC, which is equal to 7. Beautiful. Now I'm going to redraw my draw my transform section. So, for example, so we've got ASC and AST here. So oh, what the fuck? Let me do this. Okay, that's really janky, but it'll work. Okay, so we've got our B value, which doesn't change. It's going to be 350. Our D value is not going to change. That's going to be 500 plus 50 plus 50, 600. A couple important things to note is our distance to the reinforcements. 50. See how they've given it in the middle? Then distance from the bottom is also 50. Okay, cool. So let's take a look. This thing is going to be n minus 1 ASC. So once I've done the transformation, I have to multiply ASC by n minus 1. Now this is n minus 1 AST. Now, okay, what I should have actually done was figure out what ASC and AST was first. So we have 2n20. Therefore, our ASC is equal to something 4n32. AST is equal to something. Alright, so what I'm going to do actually, I'm going to go to finals. In the past papers, they actually give you the formula sheet, which at the bottom you will see is they give you like your nominal bar diameter and the number of bars, which will correspond. So let's say you have 2n20. Yeah, that means my steel area is 620 millimeters squared. Cool. Actually, is that what we have? Yeah, we have 2n20. So this will be 620. So you don't have to go through the effort of like calculating pi on 4, whatever, d squared. You don't have to go through the effort of doing that. You can just use this table. 4n32. Holy shit, those are fat bars. Okay, 4n32, 3200. Alright, lovely. That means this one, this value up here, n minus 1 ASC will be equal to 7 minus 1 times 620. This one over here will be equal to 7 minus 1 times 3200, which I don't have my calculator, so let me do it in my head. 6 times 620. 3720 mm squared. 19,200 mm squared. Okay, lovely. So we pretty much have everything we need. Now I'm going to explain how to figure out dn now. dn. So the formula for dn is the sum of yi ai, sum of ai. So this is the area A. So we pretty much have 3 components. We've got compressive steel, tensile steel, and we've got the concrete like block, this block here. Right? So each one of these has a centroid, as we know, relative to the top. So we're gonna do everything, all our calculations on the top. So working from here downwards. So this is gonna be y. Okay. So the centroid to this bar up here, or yeah, this bar, your compressive bar is 50 mil. The centroid to the bottom bar is gonna be 550 mil. Here. And the centroid of this concrete block in the middle. So I'm pretty much treating the steel transformed area separately to our original concrete block. It just makes calculations a bit easier. That's why I'm doing it. But yeah, the centroid of this block here is, for a rectangle, obviously it's just going to be in the middle, which is from the top 300 millimeters. So what I'm going to do, wait 1 sec. Okay, cool. So I'll write it out. So I'll do 300 times I'm going to do 350 times 600. Okay, I'll explain why I did this. First of all, let me just write each of these out. Okay, cool. So that's the first, that's the numerator. So this is y. So I'll highlight it. This is y, this is yi, this is yi. So this is the centroid of each component, and this is the area of each component. So this is the area of each component. So we've got the concrete block, we've got the compressive bars, and then we've got the tensile bars. Then at the bottom is just going to be the area of each component, which is just going to be the green added together. Which, when you put in your calculator, which I actually do need this time. I think I left my calculator working. Never mind. 300 times 350 times 600 plus 50 times 3720 plus 550 times 19200 plus 3720 plus 19200. Okay, whatever you get, 316.62 millimeters from the top. So pretty much if I draw what it was, so we had 4 bars on the bottom, we had 2 bars at the top. This was 600 mm's, so it would lie just a bit below, so this is where the neutral axis is. And that distance over here from here to here is 316.62 millimeters. Any questions, any queries?
No?
This is just instrument 400 recap, so should be alright. Shouldn't be too bad. The next part is IG, so that's part 4. So I've got a weird way of doing this. I don't know if it's actually that weird, but people say it's weird. I don't know why. But you get sum of II plus the sum of what is it? AI times dn minus di all squared. Okay, I'll explain what each of these mean. So this, we're taking a look at the individual component, each of them separately, and we're just taking the centroid, we're taking the inertia about its centroid for each component. So for example, for a rectangular block, it's going to be d cubed on 12. For a circle, there's a formula for it where you're never going to deal with a circle. Even though your bars here are circular, in the case, in our case, what we do is we actually assume the moment of inertia for our steel bars is just 0, because it's so small, it contributes literally nothing. right? So if you do try calculate the steel reinforcing, the moment of inertia for your steel reinforcing bars, they're just so small. It doesn't even matter. We just take it as 0, right? So in this case, we have BD cubed over 12, but just for concrete. And then obviously you're gonna take the area. You take the area of each component, which we already did over here. We already have the areas. we found dn stays constant. Di is just each of the component centroids, right? So if I were to actually figure this out, I do BD cubed, so B is 350 on 12, plus, let's do my first shape, let's do 350 times 600 times dn, which is 316.62, minus the centroid of that concrete block, which is right in the middle, squared, plus, let's do a compressive Rio. Oh, okay, even though I said it doesn't, the steel reinforcement doesn't have any inertia, it's it doesn't matter, it's negligible. The shift that it causes, so this is what we call the parallel axis theorem, the shift does matter, right? Yeah, it does have an effect to our overall shape. So we're going to take the area 3720 times 3162, whatever that is, minus 50 all squared, plus 19200 times 316.62 minus 550 all squared. And that's the gross moment of inertia. So this is what we call our gross moment of inertia. For our concrete block, which I'm actually not bothered to, no, you know what, I'm going to figure it out. Who's that?
Oh,
Who joined?
hello, sir.
Everyone.
Hi.
I'm recording.
Oh, sorry.
Which you end up getting to be, that's a huge number, 7.67 times 10 to the power of 9 millimeters to the 4. And the units for
Sorry,
each.
what was the question again?
What was the question? This question? Hello?
What the heck?
Who was that?
Hello?
Was that Liam?
Yeah, I think so. I don't know why.
It was not Liam.
Oh,
Who was it? Alright, never mind. Whatever, dude. But yeah, that's how you figure out IG and DN. MCR is pretty simple as
I
well.
didn't choose that. I couldn't find.
Who's speaking?
that's what's his thing. She's muted. It's okay. Don't worry.
Okay. I'll go ahead and mute it. MCR, as we said, is, what was the formula for it? IG over D minus DN times FCTF minus this. So this we just take it as 0. IG we just calculated to be 7.67 times 10 to the power of 9. D is 600. DN was 316.62 times this by FCTF, which we was given 3, which you get to be 81.18 kilonewton meters. Cool. Any questions about that? Let me just check if that's correct. I was a bit off, but it don't matter. I think they kind of, it's actually correct. Doesn't matter. Q. Alright, Jen, first stage of concrete done. Does that make sense?
Yeah, I think so.
It's not too bad. It's just mainly figuring out DN and IG, which
Mhm.
I'll be honest, you don't really need for Flexure at the moment. It's more so later on for serviceability, but I just want to show it all together.
Mhm.
Okay, the second stage is where he cracks. So the important rule that I talked about briefly is the concrete on the tension side has 0 strength in area. So it provides 0 strength to the overall thing. The only thing that provides tensile strength is going to be your steel, right? So if I'm thinking about how the forces are acting from the stress diagram, I've obviously got the stress from the concrete, right? I've got the stress. I've got the stress from the concrete. I've got the reinforcing bars that like contribute to compressive strength, and we've also got the tensile strength from the bars. Okay, so this will be more important when we do the alternate stage, but our new transform section is going to look like this. It looks a bit weird, but all we've done is cut it off at the neutral axis and ignore all the tensile concrete. Yeah, not too bad. So the steps are the same. You calculate n, same. Draw your new transformed section, which looks like this. However, to calculate dn, it gets a bit difficult. Right? There's 2 methods. So the first method is doing what we did earlier. However, you're gonna have to solve a quadratic now. But like, people still do that. People are comfortable with that. Like in an exam, you don't really want to do that, right? Like sack. Like it just takes too much time. The second method is using your first amendment of area principle. Okay. Do you know what first amendment of area is, Jen?
Oh, I think so.
I think you guys briefly looked at it in shear for N2400.
Yeah, I think so.
Yeah, like shear stress is equal to like VQ on like something I.
Mhm.
Yeah, something like that. But yeah, so it's actually really, really simple, if I'm being honest. It's you take the area of your component and you just multiply by the absolute value of your neutral axis minus the distance to the centroid. So if I'm going like back to this calculation here, it looks very similar to this part here, except it just doesn't have the square. So I'll explain it through this diagram here. So in this case I've got 3 components again. I've got the concrete block, I've got the compressive steel area, and I've got the tensile steel area. Now the tensile steel area, instead of being n-1, it's just now n, right?
Mhm.
And if I want to find the Q of each of these, I'm getting gas. Each one of these components, so component 1 that I've written over here is the compressive steel. Q1 is going to be equal to, you take the area, which is n-1 ASC, and you multiply it by dn, which we don't know, minus di. So the distance to the centroid of the bars, which is usually just DSC. Cool. Same thing with part 2. You do Q2 is equal to the area of that block, which is B times dn. So B times dn multiplied by dn minus, so dn is always stays constant, di in this case is going to be halfway through our depth, which is dn on 2. Wait, that's a quadratic. Is this a quadratic or is it linear? Oh yeah, it becomes linear, I'm pretty sure. But I'll check for in a second. But this last part down here is going to be Q3 is going to be NAST times dn minus dst. Simple. Right? Then just what you're gonna have to do is, in order to solve dn, it's like a fundamental principle, like always, is that compression is equal to tension. So you take the side that's in compression, so component 1 and 2, you equate it with component number 3. So you take these two, add them together, equate it with Q3. And then you just solve for dn somehow. I'll explain this with an example in a bit more detail. And then the fourth step is something called calculating ICR. So ICR doesn't have any physical significance, right, until you reach like the serviceability part, but this is called the cracked moment of inertia. Cracked moment of inertia. It's not the moment of inertia when the section cracks. That's just not true. There's really no physical way to actually explain it. It's just a value that we use. Okay, it's like you literally calculate the exact same way as IG, except you just don't have your compressive concrete. There's nothing special about it. The only thing special about it is this, which actually I'll actually quickly explain. So with no shifting, so as we know, this only applies to the concrete, and because the concrete, the depth is a function of dn, after you do a bit of algebra and a bit of math, what you notice is you can do ICR is equal to 1 on 3 BD cubed, and when you're doing the shift, you don't have to include the shift anymore. Like, I don't even know why I'm explaining that. I'll show you with an example. Okay, question. I'm gonna use the same thing as before. So calculate this is your workshop question 2. Calculate the second moment of area for the section in question 1 at the cracked elastic strength stage. So it's pretty much find ICR. So I'm going to be working with this thing again. For N32s. This was the cross section approximately. But yeah, we're gonna have to find dn. Okay, hold on, let me think. Let's draw the transform section. So we know that n. Actually, no, we already know what the transform section looks like. Because we know it's in the second stage, I'm just gonna draw the transform section straight away, like this. So this over here is still n minus 1 ASC, which we remembered to be 3920 mm squared. Let me double check. 3720, close enough. Then this thing over here is NAST, which I'm actually going to have to recalculate to be 7 times 3200. 22400 mm squared. Now the tricky thing about this is dn is unknown. This is still 350. Then the distance from here to the center is 50. Here to this center is 550. Okay, cool. Now we're ready to do our calculation. So I'm going to find Q, so let's say for compression, no, that's not that important. I'm going to say that this is component number 1. Component number 1, just breaking it off here. Component number 2, component number 3. So for component number 1, I'm going to say that Q1 is, I'm using the second method by the way, I'm not doing the first way, it takes too long. I'm going to say it's going to be equal to n minus 1 ASC times dn minus dsc, which is 3720 times dn minus 50. Component number 2, Q2, is going to be equal to 350 times dn on 2, which is just 350 divided by 2, 175 dn squared. Component number 3 is Q3. I joined. It's going to be NAST times dn minus dst, which is equal to 22400 times dn minus 550. Now we're going to have to equate these two, so this is compression, to our tension side. So we get 3720 times dn minus 50 plus 175 dn squared is equal to 22400 dn minus 550. Okay, so this one's a quadratic. What the hell? That means the one earlier is a cubic. So this actually is a cubic. So yeah, obviously you don't want to solve a cubic. So do it this way, it's a bit better, I guess. Blah blah blah. You get dn. I don't have time. dn is equal to, let's check, 202.7 first one area. Yes, I did that. Okay, cool. Lovely. So yeah, you get 202.7. Okay. Now the second part of the question is actually to find ICR, which is the sum of that plus AI dn minus di squared. So the hack I was talking about is that for the concrete, all you need to do is bd cubed, 1 and 3 bd cubed. Oh my god, my mic just fell off. Then plus, now the shift, the only thing you have to consider is the steel. So you got to take a look at n minus 1 ASC times dn minus dsc all squared plus NAST dn minus dst all squared. And that's, instead of considering that shift for the concrete, you don't really have to care about it now. The other way you can do it is just do it normally. You just take bd cubed on 12 and you also include the shift due to the concrete, but I'm not going to do that. Times 350 times d, it's actually going to be dn, sorry, dn, 202.7 cubed plus 3720 times 202.7 minus 50 all squared plus 2240 times 202.7 minus 550 all squared, and you end up getting 3.8 times 10 to the power of 9 mm to the 4. The calculation, you can like give it a go yourself, but yeah, these are the solutions here. It's a bit blurry. Can you guys see? It's a bit blurry. Jen?
Yeah, you can see.
Okay.
Yeah.
Does that make sense? Do I have to re-explain anything? I'm happy to re-explain.
I think it's alright. It's just
It's just math. Like,
yeah.
it's just Eng 2400, but a bit on crack. If that makes sense.
Mhm.
Yeah. Because the only thing that changes is like what section do you have to consider, how do we consider him, but then plugging in the values is actually easy itself. Like plugging the values here is easy, but like understanding where it kind of comes from is a bit difficult. So there's one more stage. So that's cracked stage done. Now, before I jump into the ultimate stage, there's a few key assumptions that you're gonna have to actually understand. So I've already talked about this, but first one is your compressive forces is going to be equal to your tensile forces. So this is what the force diagram looks like. I'm going to explain it later on. So down in my diagrams here, I've kind of explained what it looks like. Your internal moment is equal to your external moment, or like that's where it fails essentially. Sorry, your internal moment should be greater than or equal to. Sorry. And like you can have a reduction factor here if you want as well. Cool. And obviously your external moment, it's the maximum out of 1.35 g plus 1.2 g plus 1.5 q. That's a requirement from AS 1170.0. And the way we calculate all of these is from AS 3600. Okay, this other part was kind of explained in Eng 2400 as well. Plane sections remain plane. Whatever the hell that means, like I don't know. But the main thing that we're gonna extract from here is that later on, when we're working with our strains, let's say this is our, as I said earlier, that the compressive ultimate strain for concrete is 0.003. So that's this value here. And we know that we have compressive bars. So we've got compressive bars here, and we've got like tensile bars here, right? At each of these points, we also have a certain strain value, which, as we know, this is dn. Using similar triangles, we're actually going to have to figure out what this value is. So I'll give you a quick example. Actually, I'll just use this example right here. So let me make this a bit more clearer. So from here to here is dn. From here to here is going to be dsc. So if I take, and we know that from here to here is 0.003. So if I'm doing similar triangles, so let's take that top triangle for example. This is 0.003. From here to here is dsc. From here to here is dn. What I'm trying to find is this length here, sc. So I'm going to do this over d. That's incorrect, sorry. This is dsc. I'm going to do, so I have to figure out this length, which is easily figured out. dn minus dsc. Watch out. What happened?
That was my sister, don't worry.
Oh, okay.
Sorry.
All good. Over dn. So pretty much I'm taking a look at this triangle, comparing it to this triangle, the similar triangles, right? So this is the value that's unknown. Everything else is known. So later on, I'll show you where we need this later on. So this is going to be 0.003 times dn minus dsc over dn. I'm running through this really quickly because we're running out of time. But this is something we're going to need. Where is it? Down here. I'll come back to it, and I'll probably re-explain how to get this part as well. But shit. Okay, cool. Ultimate stage. Let's look at it. We've got, as I said earlier, we've got a nonlinear distribution. So some guy, some researcher, I'm pretty sure I think he's my supervisor. It might be him. Might have been someone else. Maybe one of his friends. I'm pretty sure. I remember in 2018, in the new revision of AS 3600, they introduced something called the rectangular stress block. Rectangular stress block. Right? Because our stress distribution is nonlinear, what this guy figured out was a way to make the stress distribution linear. So our calculations become a bit more easier. Before that, they were like doing a bit of iterating to figure out what dn was. It's a bit difficult, right? But there are two factors now that we use, alpha 2 and gamma, to kind of make this into a rectangle. So first things first, we take f dash c and we multiply by alpha 2, right? That kind of gives us this value. Then we take dn and we kind of reduce it by gamma, or we multiply it by gamma to kind of reduce it. So you can see that the stress distribution doesn't go all the way to the neutral axis. It kind of ends a bit early. But the amount of force that's acting through this rectangular stress block is equivalent to what's acting through this nonlinear distribution, right? So thing is, like, you don't need this, you need this, okay? And pretty much what happens is, as you know, for a UDL, for a pressure distribution, whatever, you get a force out of it. So this force will obviously, for a rectangle, will be acting in the middle, and it will be equal to this value, so this width times this height times the width of the actual material, B. That's the force itself. Anyways, alpha 2, this is your formula for alpha 2, this is your formula for gamma, and this is what I was talking about. This is the force diagram. CC over here stands for the compressive force due to concrete, which is this thing here, this UDL, the stress distribution. That's why I put it in red. This blue thing, these blue forces are actually forces from the steel rebar, from the steel Rio. The compressive, and they actually act at a distance, like at the centroid of the bars. So this one will act here in a compressive way. So CS stands for compressive force of steel. This one is going to be tension, because obviously it's on the tension side. So this is going to be tension steel, tensile force of steel. Okay, and as I showed you guys earlier, that the strains at each of those points can be calculated as well. So I'm going to say that from here to here, SC, from here to here is ST. And using similar triangles, you can figure it out. But the steps are a bit different to what we did earlier. Okay, to figure out dn, it's actually a bit harder. Maybe not harder, but it's a bit more lengthier. So first thing is actually an assumption step that we're going to have to do. So we're going to have to assume that our tensile steel, so the bottom steel, is yielded, right? What that means, I'll come to it. And our compressive steel is not yielded. Okay? Now, first step, this is just find dn. But there's actually some sub-steps to it. So you're going to have to first calculate, sorry, that's wrong. That should be alpha 2, sorry. Calculate gamma and alpha 2. So the formulas for that are up here. Calculate CS, CC, TS. So CS, as I said earlier, comp steel. This is compressive force due to concrete. And this is tensile steel. So because we assumed it's yielded for steel, we follow this very simple formula, AST times FSY. Kind of flashbacks to steels, if you remember. CC, as I said earlier, is you're just taking the volume of the stress block. Okay, I'm getting into a bit more theory, but all you have to know is this is what CC is equal to. Right? You take gamma, multiply by dn, alpha 2, f dash c, and you just take the width. So the only unknown in this case should be dn. Okay. Now this one we've actually assumed it's not yielded, so we can't just say that CS is equal to Fs times ASC. FSY because it's not yielded. So the bit of a nifty thing is this FSY. If we use FSY or like this letter F, it usually means it's yielded. If we use the value of sigma, because they both represent stress, right? The F and Fy stands for if it's yielded. We usually use sigma value, sigma notation when it's not yielded. Okay, so that's why in this formula I've used sigma, which is equal to E times strain. So this is a formula that we all know and love. And this part over here, as I said earlier, is equal to 0.003 times dn minus dsc all over dn. And the explanation for that, I'll actually go through it again because it's a bit weird. So you've got your comp steel here, you've got your strain distribution like this. This up here is 0.003, and at this point here we've got that. From here to here we have dn, and then to the center of the bars we have dsc. So if I draw out a similar triangle or similar triangles, oh wait, why don't I just make it like look nice? So this missing side of this triangle, so this triangle here, is going to be dn minus dsc. So we've got one triangle here with an unknown side, and we've got another triangle up here with both known sides. So I'm going to take 0.003 all over dn is going to be equal to our unknown, which is, that should have been SC. Epsilon SC all over dn minus dsc. So just rearranging for SC, 0.003 times dn minus dsc all over dn. And that's how we get it. Okay. The important thing is in the next step. Here it is. So we're going to equate our compressive and tensile forces. As I said earlier, compressive forces is equal to tensile forces. So we're going to do CC plus CS is equal to TS, and you just solve for dn. So dn only appears in this thing here, so it should be a straightforward equation. Shouldn't be too hard. It's a linear equation. It's pretty chill. Once you find dn, however, you're going to have to check your assumption. Right? So if a steel bar is yielded, that's my steel bar, if it's yielded, that means the strain in the bar has exceeded the yield strain. So if you remember back to last week, Shiba, that's the wrong one. Over here, this was the yield strain that I was talking about. So it occurs at yield stress and along this linear line. So that value, if I go back, this value is going to be equal to FSY all over ES, which is usually going to be 500 divided by 200 times 10 to the power of 3, which is 0.0025. It might change depending on what your FSY is, right? But yeah, pretty much for each bar, you're going to have to check if the strain at that point, so the strain at this point and the strain at this point, so one for your tensile bar, here, ST, and then SC. You're gonna have to check two things. You're gonna have to check whether this isn't yielded, because we assume that it's not yielded, and ST is greater than. So SY. So you're gonna have to check for your compressive bar, it's not yielded. For your tensile bar, it is yielded. So down here, that's what I've written here. For your compressive, make sure it's less than this. For your tensile bar, if it exceeds, that means it's yielded, which is good because it checks without assumption. If one of them is not true, you're gonna have to reassume. So let's say this one actually did yield. Usually this one will always yield, don't worry. But let's say this one actually yields, okay? We're gonna have to go back to the start, and we're just gonna have to fix this up. So if it is yielded, we're just gonna be like, okay, CS is gonna be equal to FSY times ASC. Cool. That's the only change. Then you're gonna recalculate DN and check your assumption again. Okay? It's you're always gonna have to check your assumption whether it's true or not, or else you're gonna lose marks. Cool? Yeah, I promise we're nearly done. Just a couple more steps. Okay. After you've checked your assumption. Oh wait, my headphone's not working. What the fuck? Sorry, I didn't hear anything you guys were saying for the past like 2 minutes. Did anyone say anything?
That's okay. No one said anything.
Thank God. Okay, cool. MU. So this is our ultimate moment. How do we calculate our ultimate moment? You're gonna have to take the sum of moments about the neutral axis. So if I draw my force diagram again, I'm gonna draw it a bit thick this time. So I've got my compressive concrete, CC. I've got CS and I've got TS. These should be flipped around, sorry. But anyways, all I'm trying to say is that from here to here, your distance is DSC. From here to here, your distance is DST. Let's say my neutral axis is somewhere here. This should be moved up a little actually. Yeah, SAC doesn't matter. Now, if you remember my stress distribution here, this force over here is going to act midway through this height, which is gamma dn on 2. So the force at this, the distance that this force is going to be acting at is gamma dn on 2. Actually, I'll make my diagram a bit more neat. I'll say sac that. This goes here, this goes here, this can go here, this can go here. So we know that this is dn, this is gamma dn on 2, and we know that this is dsc, dst, sorry. Okay, so if we're taking moments about the neutral axis, everything's moving in the same direction, so everything's positive. We're gonna have to figure out the lever arm, so we're gonna have to figure out what this distance is. Holy shit, there's cricket on the wall. Okay, bye. We got this distance, we need to figure out this distance, and we need to figure out this distance, which honestly is pretty simple, because wait, let me fix this up. This is DST, because this distance, first of all, is just going to be DST minus DN. Pretty much this thing is DST, this thing is DST, and you're just removing this part here, which is DN. So this part here is DST minus DN. I'll do this to make it a bit, give me a bit more space. This distance is pretty easy as well. It's going to be dn minus dsc, because dsc is up until here, and the rest of it, if you just take that distance, it's just going to equal to dn. So I've taken this whole distance minus this little distance, which leaves me with dn minus dsc. And finally, this one's a bit odd. This is going to be dn minus gamma dn on 2. This is gamma dn on 2. This is the lever arm. Does that make sense?
Yes.
Are you sure?
Yeah, there's a lot going on, but yeah.
Okay. Are you familiar with moments?
Yeah.
Okay. What I'm doing here, so this is the forces, and this purple thing is just the lever arms.
Hmm.
Have you done geotech?
No.
Okay.
Next year.
Next year. This thing is no, it's not really even related to geotech, but yeah. Ugh, if I'm taking moments about, so this is the force, and this is going to be the lever arm around this point, right? Because I'm taking the moments about the neutral axis. Then I've got this lever arm here for this force, which is going anti-clockwise. Then I've got this lever arm as well for this force. So all I've done, the purple thing, is the distance, is the lever arm of the force. It's just the distance between the force and the neutral axis. So purple, distance between NA and force. And then pretty much when you do MU, when you figure out MU, do the sum of moments about NA, which is going to be, you take the force, CC, multiply by the lever arm, which is dn minus gamma dn on 2, plus CS times dn minus dsc, and then finally your TS times dst minus dn. Okay, and that's how you figure out your value for MU. Usually this, like, you can probably use this as like a general equation, usually. If you don't, obviously if you don't have compressive steel, then you just let this be 0. Okay. I can explain this later on with like a proper question, but I think probably not. It's probably best not to go through it right now. But a couple more steps. I think 2 more steps. So once you figure out MU, so this is your formula for figuring out MU. Right. You're gonna have to check something called ductility. So this is what I was talking about. DO. It's the depth to the outermost steel. So let's say you have two rows again, right? DST is going to be in the centroid of that shape, the 4 bars, but the DO is going to be to the outermost bar, which, yeah, you just plug it in, you do dn over do. There's 2 cases. It's either below 0.36, which is what we want, it's a ductile failure. If it's greater than 0.36, then we need to add ductility, or we need to add compressive brio to it. Okay, so one way to actually increase ductility is by adding compressive brio. The reason for that is because it decreases our dn. So if you remember earlier, I said that your neutral axis will shift towards like the heavier side. So let's say I've got something like this. I've got no compressive bars. Okay, so Jen, a question for you: will the neutral axis, would it rather be up here? Does it make more sense for it to be up here, or would it be down here?
With the compressive bars, it's there.
Like let's say we just have tensile bars.
Yeah.
But would it make sense for the neutral axis to be down here somewhere? Or up here somewhere?
I got no idea.
Okay, that's all good. So it would make more sense for it to be down here. Because it's getting shifted downwards by the steel.
Okay.
So imagine you just had a concrete block, it would just be in the center.
Mhm.
But because we're adding some weight down here, it's going to get dragged down. And your ductility formula, it's a function of dn. So if you want to minimize our ductility, all we have to do is decrease our dn. So pretty much bring our dn closer to the compressive side. The way we do that is by adding compressive steel. It's probably not going to make sense anymore, but you can probably just, it's a bit late. You can come back and watch later, and hopefully it makes more sense. That's so good. And then finally, you just figure out your capacity reduction factor, and you check, and you're done. So this is usually the steps that you would take to figure out, for like an exam style question. I'm not going to go through this now because it takes a really long time. But let's say you weren't given a section. So you weren't given, this is 350, this is 600, you have compressive bars here, you have tensile bars here. Figure out MU. Let's say you weren't given any of that. Let's say you literally, the only thing you were given is what the beam looks like, right? Like from here to here, it's like 8 meters. From this, design the beam, design the section, right? That takes a really long time to do, and something I'll explain next week. But it's a bit of guess and check work. That's a problem with it. It's a bit of guess and check work. But the formulas themselves are pretty it's pretty much the same. We come back to initial sizing in steels, right? A bit of a trigger word, but we're gonna have to do a bit of that, and yeah. Cool. Okay, I'll leave it there.